Good. Please just put it down. Yeah, that's fine. Okay, so the purpose of the problems is for you to practice, learn, because a lot of stuff, there's just not enough time to actually teach in lectures, so you have to learn it by doing the problems. So, for example, the functional equations problem set, you'll learn a lot of functional equations techniques by doing it. Because for functional equations, there's not a lot of theorems and stuff that you can apply onto a function. There are also links to the problems that you can go to if you get stuck, but please work on the problem for a good amount of time before having a look at the solution. So, functional equation problems for yesterday. Today we're doing polynomials, and tomorrow we'll do inequalities. Good. So, any further questions? Not yet. Okay, so you have probably encountered polynomials before, but I'm going to assume that you haven't and just tell you polynomials from the beginning. So one way to look at it is that a polynomial is a special kind of function. And another way to look at it is actually as an algebraic object. So first of all, if you want to work with polynomials in general, I'll quickly tell you what a field is and what a ring is. A ring is not the one that you wear on your finger. We're talking about mathematical ring. And a mathematical field is not, wait, which direction is it? Not that one over there through the door. So these are different names. So a ring, without going into the exact details, it's basically any sort of set of, you can think of numbers, but they can be more general objects. Some sort of set where you can add things, you can subtract things, and you can multiply things. So if you can do those things, then you've got a ring. And there are conditions that addition and subtraction and multiplication have to behave the way you're used to them behaving. Like if I have a plus b, and then I add c onto that, that should be the same as adding b plus c and then a onto that. So all the usual behaviors of addition and multiplication are the way that you're used to, except that in a ring, multiplication isn't always commutative. So if I have a times b, that is not always the same as b times a, in general for a ring. So this multiplication isn't necessarily multiplication of numbers, it could be multiplication of something else. But today, for now, we're going to be dealing with commutative rings. And for commutative rings, multiplication does commute like this. So a times b is the same as b times a. Okay, so examples of rings. A lot of subsets of numbers are rings and a lot of them are not. So the integers is a ring. You can add stuff, subtract stuff, multiply stuff, and you don't go out of the set of integers. Okay. Is the natural numbers a ring? Yes? No? No? No, it is not a ring, because when you subtract two natural numbers, it doesn't stay a natural number. Well, not all the time. Okay, so that is not an example. How about the rational numbers? Is that a ring? Yes, you can add, subtract, multiply, it's all still good. Okay. Now a field, the conditions are, I could just write them all down again, but I'll just say, first of all, it's a ring. But also, and actually for a field you need it to be a commutative ring. So multiplication behaves similarly to normal numbers. A times B is the same as B times A. And the extra condition is that you have to be able to divide things. So, examples, rational numbers is a field. Real numbers is a field. Complex numbers is a field. Is the integers a field? Nope, no it is not. If you divide two integers, it doesn't always give you another integer. Okay. So, if you want to look at polynomials as algebraic objects, one way to look at it is as follows. If I have any ring, let's say I have a ring R, so you can think of this as a set of numbers like integers, rationals, reals, as long as you can add, subtract, and multiply. If I have a ring, I can make another ring out of that, which is called the ring of polynomials. So that leads to the ring of polynomials, which is denoted your R together with a variable like that. And this is the set of all functions that look like the following. It's got a0, a1x, a2x squared, up until some highest degree, where each of these a0, a1, up until an are in your original ring. So one way to look at it, look at this expression is as an algebraic expression. You're adding stuff, you're multiplying stuff. Powers just mean you're multiplying repeatedly. Another way to look at it is as a function. So this is a function of x. And you can put in a value of x, you can get another value out. Some terminology, these ai, so a0 up to an, are called the coefficients. Some of them can be 0, so they're allowed to be any elements in the ring. Usually the biggest one, or the one corresponding to the biggest power of x, we usually assume that one to be non-zero, because if it's 0, you're adding 0, you can just consider the ring or the polynomial with one less degree. So if this biggest coefficient is not 0, then the degree of the polynomial, actually I haven't given this a name, so I'll call this polynomial, this whole thing, p of x. So the degree of p of x is the exponent of the biggest exponent of x. And
so when you say R of x, you're referring to a bigger set, are you?
Yes.
And the P of x is just that specific example within the bracket?
Yes, so P of x is one particular polynomial that I'm now talking about. So the degree of P of x is this, and an is the coefficient of the biggest power of x. That's called the leading coefficient. reminds me. An is the leading coefficient, and the A0 is the constant term. Okay, so that's some terminology. So moving a bit away from the abstract towards more concrete examples, if we replace the ring R with specific polynomial or with specific rings, we can have the ring Zx, which is all polynomials with integer coefficients. Or I can have the ring Rx, which is all polynomials with real coefficients, and so on, complex coefficients, whatever. Now, I called this a ring. I mean, I've been saying that the set of polynomials with coefficients in another ring, that set is itself a ring. In order for it to be a ring, I need to be able to add, subtract, and multiply polynomials. I'm sure you guys know how addition, subtraction, and multiplication of polynomials works. Yes? Good. So this is in fact a ring. Okay, so that's some terminology. That's the degree. That's the constant term. I think I'll illustrate some of these with problems where you would use the degree of a polynomial in order to solve the problem.
Is it possible to define a field of polynomials where the denominator divides into the numerator?
So for a field, you need to be able to divide any two elements, even if the denominator does not divide into the numerator. So if you just stick with polynomials, it's not a field. But if you go to a bigger set, the set of all rational functions, which is basically polynomial divided by polynomial, then that is a field. Okay.
Liam,
Yes.
how do you, for fields, so you said dividing any two numbers. So,
Except for 0.
Okay, so you consider none. Yeah.
Okay. Now, I'm going to pull some of the problems in the problem set that I gave you and just use them as ways to illustrate these concepts. So with a functional, usually a functional would be find all functions from this set to this set which satisfy some equation. Usually what a functional looks like. Polynomials are sometimes the same. Sometimes it would be find all polynomials which satisfy some relation. Or sometimes it's a more complicated case. But usually the fact that you're told that something is a polynomial, it immediately gives you more information to work with, because polynomials can be seen as a special subset of functions. So usually the polynomial equation they give you, you wouldn't be able to find all functions that satisfy that, but you can find all polynomials that do. So here's a first one. I think it is number 5. Find all polynomials P of x and Q of x
Real coefficients.
with real coefficients such that the following is true. P of Q of x is equal to P of x times Q of x for all real numbers x. Okay. Find all polynomials for which that is true. Probably the best way to solve this is to look at the degrees of your two polynomials. So let's say, let the first one have degree n, and the second one, q of x, have degree m. Then first of all, what is the degree of p of x times q of x? 2%. By the way, a little notation. We would usually write DEG, like sine or cosine degree of a polynomial. So degree of p of x, q of x would be m plus n. The reason for that is you have one polynomial like this, where biggest power is n, another polynomial, the biggest power is m. You multiply all the terms out, the biggest power in the product would be the biggest power in the first one times the biggest power in the second one. And x to the n times x to the m is x to the n plus m. Okay. What is the degree of p of q of x? Yes, that is going to be m times n. And why is that? Well, you're taking, if let's say this is p of x, you're putting q of x in the place of x. So that's a0 plus a1 q of x, a2 q of x squared, up until an q of x to the n. And the biggest term in the biggest power of x in each of those, here would be 0, here it would be m, which is the degree of q. Here it would be m or 2m, which is where m is the degree of q. Here it would be, you would have q of x to the n as the last term here. And q of x is a polynomial where the biggest term is x to the n. That whole thing to the power of n. The biggest term in that big product would be x to the m to the n, which is x to the mn. Okay. Now you're told that this polynomial is equal to this other polynomial for all values of x. And this is perhaps a subtle distinction, but it's worth actually keeping in mind. If you're told that some polynomial thing is true for all real values, that means that the two polynomials on either side are actually equal as polynomials, not just as in terms of the function values that they give out. So yeah, if you know polynomials as abstract objects, that's not an easy thing to immediately see, but you can gloss over that. So we know that that polynomial is the same as that one, which means that the degrees on each side are equal. So mn is equal to m plus n. How can we solve this?
M equals n equals 2.
Or n equals n equals 0. Those are both.
Okay, so how do we solve it? Not just what is the answer.
You can solve for either m or n, create an expression, and it's easy to see that there's only one answer.
Cool. So you can solve for m, take that to the other side, you get m equals n over n plus 1, and then that has to divide that. So that's one way to do it. Another way to do it is to take that over and add 1 on each side, get m minus 1, n minus 1 equals 1. Either way gives you the same answers. what you do know is that m and n are non-negative integers. So here's an integer multiplied by another integer giving you 1. Basic number theory, the only way that happens is if this is 1 and 1 or negative 1 and negative 1. So either m and n are both 2 or m and n are both 0. Yeah?
So are integers also polynomials with degree 0?
If you have a polynomial where all of those are gone and you only have a0, that is a polynomial. Yes. So we end up with that either m and n are both 2 or m and n are both 0. So either p and q are both constant polynomials or they are both quadratic polynomials. If we do the simpler case first, so m and n both equal to 0, we do that case first. So p of x would just be some constant. Give me a letter.
C.
C. Q of x would be some other constant, which is d. Okay. Then what would p of q of x be?
C.
Yeah, only c, and the other side you would have c times d. So either c is 0 or d is 1. And those are actually independent. You can have c equals 0 and d doing whatever it wants, or you can have d equals 1 and c does whatever it wants. So in this case, your solutions are, if c is 0, that means p is actually the 0 polynomial. So either p of x is always 0 and q of x can do whatever it wants, and you can check by putting that in there, that is a valid solution if just p of x is constantly 0, or if q of x is the constant 1 polynomial. That also satisfies, well, that satisfies this as long as p of x is also constant. Okay, so those are the two solutions in that case. In the other case, we have that both of them are quadratic. So let's suppose that p of x is ax squared dx plus c. Q of x is dx squared dx plus f. Okay. Now we've looked at the degree, we've used that as much as we can. Let's also look at the leading coefficient on each side. What would the leading coefficient of p of q of x be?
AD squared.
Yes, AD squared. And the leading coefficient of p of x times q of x would just be AD. Because these polynomials are equal, that is equal to that. And so we get that d is equal to 1. Any objections? No? Okay. Yeah, we divide by AD on each side, so we get d equals 1. Okay, so that helps a bit. Let me not rub it out. So we know that this is 1. Let's also look at the constant coefficient. So the constant term. Okay, what is the constant term of p of x times q of x? That would be cf. And p of q of x would be something less simple.
A is squared plus BF plus C.
Yeah. So it seems like we're making some progress with finding out these coefficients, but we still have a lot of work to do. One way is to get a system of equations by actually plugging in p of q of x and actually multiplying out the whole polynomial. You get a 4th degree polynomial on that side. Multiplying p and q, you get another 4th degree polynomial on that side. In order for them to be equal, the corresponding coefficients have to be equal. You get 5 equations, and then you solve for that, which some people say is not fun. However, okay, I'll come back to this problem later once we have a bit more ammo. Yeah, we'll come back to that. Then we can more easily narrow down what the coefficients are over here. Okay, so for polynomial, we have degree, we have coefficients, leading coefficients, constant terms, and we've seen how degrees behave when you multiply and compose two polynomials. Adding two polynomials, well, it's usually the degree of the bigger one unless they happen to cancel out. Next, let's look at the roots of a polynomial. Okay, so roots of a polynomial, like roots of a function, is where that polynomial is equal to 0. Any value where you put it into the polynomial, you get 0. First thing to note or notice is that if r is a root, so if p of r is equal to 0, then you can actually start factorizing the polynomial. X minus r is a factor of the polynomial p of x. Using the same notation divides here as you would use in number theory by saying one number divides another number. The reason I'm doing that is because the integers, in terms of the way number theory works with one number dividing another one, it works very much the same with polynomials. You can still define one polynomial dividing another one, just meaning that this one can be written as this times another polynomial. And you can define prime polynomials. You can do some sort of fundamental theorem of arithmetic where you decompose a polynomial into a product of prime polynomials. So a lot of it works the same. So this is a special case of another result which you may seem familiar as well. Have you guys done Euclid's division algorithm for natural numbers or for integers in general? So this is pretty much the same. So Euclidean division algorithm for polynomials would be, if I have one polynomial p of x and I have another polynomial q of x, then I can always find another polynomial. Okay, first of all, these need to have coefficients in a field. So let's say real numbers, coefficients in the reals or complexes or rationals.
Also, if you can just do the Euclidean again just for a real number. Or
For natural numbers. Okay, sure. So the Euclidean division algorithm for natural numbers would be the following statement, that if I have one number, let's say I have a number p and q which are integers, let's say q is positive. Actually no, p and q are not good examples here. Let's say a and b are integers and b is positive. That's the situation, and then the Euclidean division algorithm tells you that there are two other integers, q and r, such that the first one, a, can be written as q times b plus r. So far, not much importance over there. And the important thing is that r is between 0 and b. So the idea is, no matter what size a is in terms of b, I can write a as a quotient times b plus a remainder, where the remainder is small, between 0 and b. So that is the Euclidean division algorithm or statement for integers. Corresponding statement for polynomials, let's rather call this, for analogy, I'll call them a of x and b of x. There exists another polynomial q and r of x with coefficients in the same field, such that a of x is q times b plus r, and the degree of r is less than the degree of b.
So, Liam, sorry, are you referring to these polynomials now as fields?
They have coefficients in the field.
Ah, okay.
So this f could be real numbers, complex numbers, rationals usually.
Okay.
If you want to be fancy, you could do like Gaussian rational numbers. Some people like fancy stuff.
But when you write a of x comma bx is an element of f of x,
Yes.
the implication then that it's the coefficients that are in f.
Yes.
Okay.
So this means that it's a polynomial with coefficients in f. Okay, so if I have a and a b, usually we would have the degree of b is less than the degree of a. I can always write it as a quotient plus a remainder, where my remainder is smaller than b. Here, because we can't, like with integers, we can just say one number is smaller than another number. Polynomials, the idea of smallness we use is by measuring the degree. So the degree of r is less than the degree of b. Okay. So, in particular, I can show how to use this in order to derive that if a polynomial at r is 0, then x minus r is a factor of that. So, as an example, I'll take the polynomials p as my bigger polynomial and x minus r as my smaller polynomial. So I can always write p of x as x minus r times some other quotient plus a remainder. And we know we can always do this in such a way that the degree of r is less than the degree of this.
Would it always be one less, or generally speaking, one less?
Most of the time one less, but it can be less than one less.
Yeah, obviously if the coefficients are 0, but in general it's one less. Would be more,
It can be like,
or the same.
if b is actually a factor of a, then this is just going to be 0. So,
Okay.
like probabilistically speaking, it's most often one less, but it can be much less than one
But
less.
it's never more. It's because it's
Yeah.
always less.
Yeah, because we have that condition, the degree of r is always less. So in this case, the degree of r has to be less than the degree of this polynomial x minus r. And the degree of that polynomial is 1. So the degree of r is less than 1, meaning that r has to be degree 0 or a constant polynomial. R is constant. So let's say it's always equal to some specific number. Now, I have to use the fact that P of R is equal to 0. So let's plug in x equals r into this equation over here. 0 is P of r, which would be, so here we're going to have r minus r times q of r plus this constant r0. That is a 0. So the only thing left is to tell us that this constant we're dealing with is actually 0. So this polynomial r is always constantly 0. So if I rewrite this equation we have, p of x is x minus r times q of x. R of x is constantly 0, so that goes away. And here we have that x minus r is a factor of p of x. Good. Now you can extend this sort of argument to, I mean, the idea is that we have one polynomial x minus r, and whenever this polynomial x minus r is 0, then p is also 0. So you have two polynomials. Whenever the one of them is 0, then the other one is 0. And the result we get is that the one has to divide the other. So can we say this is true in general? Can we say, let's say we have a polynomial p of x and another polynomial q of x. Can we always say that given the following information, when p of x is equal to 0, that implies that q of x is equal to 0? Can we then say that p of x is a factor of q of x, given that information? Can you think of any counterexamples? Oopsie. Well, one example where that implication doesn't work is if p of x is x squared and q of x is the identity polynomial x. So here, if p of x is 0, then x squared is 0, which means x is equal to 0, which means q of x is 0. But p as a polynomial is not a factor of q. But you see, the issue here is that we have a repeated root. Here, x is a root of p in a sense twice. Because if you factorize p, you've got an x, a 0 as a root, and you've got 0 as a root again. So we can make the following statement, and we can prove it basically using the same procedure as down there. That if p of x is what they call is square free. In other words, it has no square factors inside it. And whenever p of x is 0, we have that another polynomial is also 0. Then p of x is actually a factor of q of x. So I can write q as p of x times another polynomial. Yes.
Could you just explain again what you mean by if p of x is 0, so that implies that q of x is 0?
If this is always true. If we have polynomials p and q such that this is always the case. When p of x is 0, q of x also happens to be 0.
I see.
So
Okay.
p of x might be 0 when x is 1, 2, and 5. And it so happens that q is also 0 at 1, 2, and 5, and maybe some other values as well. So we're assuming we have a polynomial p and q which satisfy this statement. And we want to say that p divides q. And that's generally only true when p is square free. Yes?
Is this only if q is a non-zero polynomial, or do you say p divides 0?
For integers, does 5 divide 0? What do you think?
Yeah.
What does the audience say? Does 5 divide 0? Yes. And same is true for polynomials. The 0 polynomial is divisible by any other polynomial. Good. Okay, I'm going to have to fly through the rest of this. So, a very important thing about the roots of a polynomial related to the degree is that a polynomial cannot have too many roots. So if p of x, a polynomial, has degree n, then your polynomial p has at most n roots. Yes.
Real roots, or isn't it does have n roots of one description or another?
So it does.
Either repeated or complex.
Yes, it does have exactly n roots
Yeah.
if you say complex and you're counting repeated roots as well. So this is, like I mentioned yesterday, the real numbers are not the best field. Best field is complex numbers, because in complex numbers you can say that if p of x has degree n, then it has exactly n complex roots. So that's nice. So how can you use this? Well, many times in a polynomial question, you would have some polynomial, let's say p, has a particular degree. Let's say you have that the degree of p is less than or equal to n. It's at most something. And you manage to find more than n roots for this polynomial. So if you find R1, R2, you find a certain number of roots, possibly even you manage to find infinitely many roots for this polynomial. So where m is greater than n. The only way that can happen is if p is always 0. So in terms of degree, the zero polynomial is it's almost a special case because it has infinitely many roots because it's always 0 no matter what you put into it. So it's a special case. Some people would say the zero polynomial has degree 0. Some people would say it has degree infinity or negative infinity, depending on how you order things. But this is a classical polynomial strategy. You have a bounded degree and you manage to find more than a certain number of roots, therefore your polynomial has to be constantly 0. Okay, last thing I'd like to say, which is perhaps a simple observation, or second last thing I'd like to say, which is actually very important for today's question 5. Basically the only observation you would use is the following one. So if you have a polynomial with integer coefficients and you have two integers a and b, then a minus b divides p of a minus p of b. Here it divides in terms of integers because p of a is just an integer. You evaluated p at an integer. P of b is another integer. P of a always divides p of b. One way to see this is to just write out p with integer coefficients, say that minus that, and you have difference of n's powers, and a minus b is a factor of each term that you get. And this is actually the key observation that gets used in many problems with polynomials with integer coefficients. If you see a polynomial with integer coefficients, chances are you need to use this. And you might get the solutions late for today's test later today, in which case you would see how this gets used in such a problem. Good.
So the a and the b are arbitrary values.
Yeah.
And so just choose any arbitrary values and subtract one from the other, and it'll be divisible by the difference between the functions.
It'll divide into the
sorry,
difference
yes.
between the function values, yes. Good. And then the last section I'd like to speak about is,
Sorry,
yes?
Can you just maybe give an example of just
An example. Okay, so there's a classic example which I think is from the USA Maths Olympiad. So let's suppose we have an integer with coefficients, a polynomial with integer coefficients. And we are given three integers a, b, and c, which satisfy the following conditions. B is p of a, c is p of b, and a is p of c. And the question is, you're asked to show that A equals B equals C. So this is possibly the easiest problem I know which makes use of this, and it illustrates it quite nicely. So A minus B divides P of A minus P of B. Because of the equation function values we're given, this is B minus C. Similarly, B minus C divides P of B minus P of C, which is C minus A, and C minus A divides P of C, P of A, which is A minus B. So you've got three numbers, A minus B, B minus C, C minus A. You want to show that these are all zero. You have that this one divides that, this one divides that, and this one divides that. So none of them can be strictly bigger than any of the others. Because if that was the biggest out of these three, it wouldn't be able to divide into that one. So they have to all have the same absolute value. So let's say A minus B is X.
Can I just ask maybe a simple question?
Yeah.
So if A equal B equals C, the only solution for that is for all of them to be zero. That to prove.
Well, yeah, you want the differences to be zero.
Okay.
Yes. So if A minus B is X, then B minus C would be plus minus X, and C minus A would also be plus or minus X. Now we want to show that X is zero. And of course, A minus B, B minus C, and C minus A, if you add them together, you get zero. And if you evaluate this modulo 2x, each of these is congruent to x modulo 2x. If this is negative x is congruent to 2x, or congruent to x modulo 2x. So x plus x, which is 2x mod x. So 2x divides x. If x is not zero, it's a non-zero integer, I can cancel on each side and I get 2 divides 1, which is not true. So x has to be 0. So all of these have to be 0, so A equals B equals C. So that's a classic example of using that property of integer. Okay, the last section topic that I'd like to do concerning polynomials involves Vieta's formulas and symmetric polynomials. I love when you have like two M's and you're doing cursive, you just go like that. Who knows what I wrote there? I don't know.
Sine wave.
Yes, it's a sine wave, or cosine, whatever. So first of all, so far we've been doing polynomials with one variable, x, y. It doesn't matter what you call it, it's one variable, x, y, g, whatever. We can have polynomials with as many variables as we want. In fact, you can consider a ring of polynomials with infinitely many variables. That's for fancy people. But let's suppose we want to consider polynomials in n variables. So x1, x2, up until xn. And I want a special polynomial with n variables. I want to have the property, so let's say this is p of x1, x2, up until xn. I want to have the property that if you swap any two of these, let's say x2 and xn, if I swap any two of them, the polynomial still stays the same. For example, if I have the polynomial of two variables, x1 and x2, which is x1 squared x2 plus x2 squared x1. If I swap x1 and x2, this expression actually still stays the same. And I want to sort of characterize all polynomials with n variables, not just two, that have that property. And this is where the elementary symmetric polynomials come in. These are usually written with the small letter sigma I of x1 to xn. There's two definitions. I'll give both of them, but they are actually the same. The first one is, okay, this is going to be a horrible sum, or rather I did out in words. So I want to say the sum of all products of I of the x1 up until xn. So I take these x1 to xn that I have, I multiply I of them together, I different ones together, and I take all possible combinations of choosing I of them, and I add all of those monomials up, and I get a polynomial. For example, sigma 3 of, let's say I have 4 variables, or should I do 5? Let's do 5. One possible way of having 3 of them together is x1 times x2 times x3. And I can just keep on writing more. x1, x2, x4, x1, x2, x5. So that is the third elementary symmetric polynomial on 5 variables. I take 3 of them at a time, multiply them together, and I add together all possible combinations of 3 of them.
Is that I the degree of the...
Yes, I would be the total degree, because yeah, each term has degree 3. Another definition is that sigma I of x1 to xn is the coefficient of, let's say, y to the I in the following other polynomial: 1 plus x1y, 1 plus x2y, times 1 plus xny. Take 1 plus each variable times y. Y is just some other dummy variable that I'm using. I multiply all of those out, and I take the coefficient of y to the power of I. You should convince yourself that that actually gives you the same answer as that.
Yes.
Good.
Because
So-
I checked on that before.
If some special cases, what is sigma 0 of x1 to xn?
It would just be an empty, just constant T0.
Well, kind of. It's actually 1 because I'm doing, okay, one way to look at it is, okay, the coefficient of y to the power 0 there, which is 1. Another way is I'm taking a product of 0 of them. What is if you take a product of 0 things, what do you get? 1. Not 0. And yeah, so, and there's only one way to choose 0 of the xi. You just choose 0 of them. So that's why you get 1. Another way is to just look at the coefficient in there. Other special cases, what is sigma 1?
Wouldn't it be the sum of all of those?
Yep, you just add all of them together. And sigma n xn, that would be the product of all of them. Finally, what is sigma I of x1 to xn if I is greater than the number of variables that you have?
It would be 0?
Yes, that would be 0.
Because there's no coefficient.
Yeah, one way to look at it is there's no coefficient with
Also, you can't
bigger
choose,
degree.
You can't choose 5 things if you only have 4 things.
Yeah, what he said. Okay, so these are the elementary symmetric polynomials. Now, why these are called the, okay, so these are the elementary ones. Elementary. So why these are called the elementary symmetric polynomials is because of any other symmetric polynomial can be written in terms of these ones. So if p, let's say p of x with integer coefficients, sorry, not just p of x, I want a polynomial of n variables with integer coefficients, x1 to xn of my variables is symmetric, then I can actually write p in terms of these elementary symmetric polynomials. In other words, I'll continue over here. There is a polynomial q of, let's say, z1 to zn, such that p of x1 to xn is equal to q of these elementary symmetric polynomials. For example, if I want the sum of squares, so x1 squared, x2 squared, up until xn squared, that is symmetric. The sum of any nth powers or odd powers is going to be a symmetric polynomial. I can write these in terms of the elementary symmetric polynomials as sigma 1 squared minus 2 sigma 2. And there's a particular identity called Newton's identity, which relates these sum of whatever kth powers, how to write them recursively in terms of the elementary symmetric polynomials. Yes?
So if the polynomial P has integer coefficients, will Q also always have integer coefficients?
Oh, yes, yes. Sorry, forgot to mention that. Q also has integer coefficients.
What if P has real coefficients?
Then Q will have real coefficients. The why integer coefficients is important is that I might choose my P to have integer coefficients and end up with my Q having rational coefficients if I choose the wrong set of elementary symmetric polynomials. But because I chose this particular set, I can also guarantee that my Q has integer coefficients. Okay, last result I'll mention using these elementary symmetric polynomials is called Vieta's formula. And that is, if I have a polynomial, let's say P of x is that, and let's suppose that I know what the roots are. In fact, suppose I don't know what the roots are, but I'm going to write down the roots. Like if P has real coefficients, these roots might be complex, but that doesn't matter. I have roots R1 to Rn. Then I can actually get information about the roots without actually factorizing this polynomial, without actually solving for x equals 0 and getting all the roots. Especially if P has high degree, it's going to be basically impossible to find all the roots of it. But I can write down some information about the roots. If I want sigma I of these roots, that is going to be equal to A n minus by An. It's that divided by the leading coefficient together with a negative 1 to the power of n minus I. Yes. So even without calculating the roots, I can get that this particular combination of the roots in terms of the coefficients of the polynomial in a very easy way. So I can tell you that the sum of the roots, I can write down the sum of the roots in terms of an minus 1 and an without actually calculating the roots. And the product is in terms of the constant term and the leading coefficient, which is quite useful. Okay, so do we have questions? Nope, otherwise that's my time for today. Please practice the problems that you have. They are for your good, and you will learn stuff.